أستاذ أبو العلا، أبو العلا سمعني؟ أستاذ أبو العلا؟ أستاذ أبو العلا سمعني؟ أبو العلا؟ Lajal, do you hear me, please?
Yeah, we hear you.
Yeah, I think we can start now. Bismillah ar-Rahman ar-Rahim. Wassalatu wassalamu ala Rasulillah wa alihi wa sahbihi. Good morning, good afternoon, good evening, where you are. Dear Professor Dr. Abu Al-Ala Hassani, the founder of Scientific Research Group in Egypt, the founder of the International Conference on Artificial Intelligence and Computer Vision, and the general co-chair of AICV21. Their colleagues, their PhD students, their attendees, ladies and gentlemen, I would like to thank you all for your participation to the second edition of the International Conference on Artificial Intelligence and Computer Vision, which is held this year virtually due to the COVID-19 pandemic situation and the travel restrictions. It was expected that this edition will be organized in Morocco in face-to-face mode. AICV21 is organized by the Scientific Research Group in Egypt and the Computer Networks, Mobility and Modeling Laboratory from the Faculty of Science and Techniques at Morocco and supported technically by Springer. The conference provides a remarkable opportunity to address new challenges, share solutions, and discuss future research direction in all aspects of artificial intelligence and computer visions. It covers topics related to deep learning and IoT, smart grid, machine learning, meta-heuristics, optimization, ontology, machine vision, robotics, speech recognition, and advanced machine learning technologies. All submissions have been reviewed by 3 reviewers on average, with no distinction between papers submitted for all conferences tracks. We are convinced that the quality and the diversity of the topic covered will satisfy both the attendees and the readers of the conference proceedings. They have already been published by Springer in its series of advances in intelligent systems and computing. For the technical program of the conference, we have 2 plenary talks and 4 oral sessions. Today, we are going to have 2 plenary talks and 2 oral sessions. Tomorrow, we will have 2 oral sessions. We would like to thank the authors for their valuable contributions and the general chairs, the conference co-chairs, the International Advisory Board, the technical program chairs, the track chairs, the reviewers for their efforts and for the time they spent on the review process of the papers, the publicity chairs, the session chairs, the Scientific Research Group in Egypt member for their assistance, and all the other chairs. Our special thanks also go to the plenary speakers, Professor Parthasarathy, Subashini, and Professor Cassie Santosh, who accepted to share with us their knowledge and expertise. We are also grateful to all our partners, especially Hassan First University, Hassan Second University, and the Faculty of Science and Techniques at Morocco. We hope that you will find the technical program of this conference very interesting and benefit, and you will appreciate the quality of all the presentations. At the end of this opening and welcome message, I give the floor to Professor Lajel Bellatrich from the National Engineering School for Mechanics and Aeronautics, Châtenoy, France, who is going to share the first plenary talk. The speaker is Professor Parthasarathy Subashini from the Center for Machine Learning and Engineering, Avinashilingam, University for Women, Coimbatore, India. The title of her talk is Improved Reinforcement Learning for Intelligent Devices. Professor Lajel, you have the floor.
Hello.
Yeah.
Good afternoon, sir.
Professor Lajel, we didn't hear you. We don't hear you. Lajel. We don't hear you, Lajel. Lajel? We don't hear you. No.
No? Hello?
Yeah, okay now.
Okay. Thank you, Professor Hakiki.
Welcome.
I am so happy to be with you. I would like to thank Professor Abul Ala, the founder of this conference. Thank you for all participants, all reviewers, authors that submit papers. I am so happy to be here with you. Even the conference is not in face-to-face, but I think we will enjoy the program of the conference. I would like to introduce the first keynote speaker, Professor Savishini. The keynote title is Improved Learning for this Device. Let me introduce Professor Subashini. Professor Subashini research has spanned large number of disciplines like image analysis, pattern recognition, neural network, computational intelligence, congruency, and she's contributed to several fields of mathematics, especially naturally inspired computing. She is co-authored of 6 books, 7 book chapters, 1 monograph, and more than 165 papers, including published in IEEE Springer and in various international venues and conference journals. In her course, he research and teaching Professor Subashini was motivated more over than 100 of postgraduate students and guiding several postdoctoral students. She had position as reviewers, chairperson for different peer-reviewed journals. Under her revision, she has 10 research projects and more than 1.5 crore from funding agency like Defense Research and Development Organization, Department of Science and Technology, and some university grants commission. She is with many countries like Singapore, Malaysia, Dubai, France, Switzerland, Italy, Canada, Germany, Spain, and Republic Czech, Italy, Morocco, United States, China, for various knowledge sharing events. As member of IEEE Computational Intelligence Society and IEEE Computer Society of India, she extended her contribution as IEEE Chair of 4 Women in Computing under IEEE Computer Society of India Council in the year 2015 and 2016. She has established active international teams with the University of USA and University of Ascendeux, Casablanca, and we saw that she has very nice connection with Morocco by executive MOT with these 3 universities. She is coordinator Center of Machine Learning and Intelligence, funded by the Department of Science and Technology of India. She is also an active research consultant for few institutions. Now you have the floor. You have 40 minutes to present your big topics about improved reinforcement and learning for this device, and maybe we have 10 minutes for questions. Please, you have the floor, professors.
Thank you, Professor Lajel, and I'm very happy to be part of this AICV 2021. And first of all, I would like to thank Professor Hakik for inviting me to this particular event, which is happening online. Though it is online, it is an international event, of course, and so many papers and so many people involved in that as committee members, session chairs, and so many professors from Hassan University of Hassan One, and also from many other universities from Seattle, everyone. And so I would like to thank all the organizers and especially Professor Hakik for organizing such kind of event even in this pandemic time. And I would like to thank once again for inviting me as a keynote speaker for this particular event. So as I actually extend my thank to Professor Ladje also for introducing me to the forum. So going into the topic. So am I audible, sir?
Yeah, please share your screen.
Yeah, you can share your screen.
Yeah, yes. Okay.
Okay, good.
One second. Yeah. So as introduced by Professor Ladje, the topic given to me is improved reinforcement learning for intelligent devices. So very much related to the conference, which is dealing with artificial intelligence and computer vision. So this topic also very much close to the intelligent devices, which will have certain kind of vision. So image processing or image vision. So I chose this topic so that the participants and other people who are actually involved in this forum can understand what is actually, can become aware of what is improved reinforcement learning for intelligent devices. So before going into the improvised learning for such kind of devices, I just wanted to introduce what is optimization first. So machine learning optimization is one of the process for adjusting the parameters in order to minimize the cost function by using any one of the optimization technique which is available or which is compatible for doing such kind of thing. So it is a problem of finding a set of inputs to an objective function which results in maximizing or minimizing the function evaluation. So the objective of any kind of optimization problem is either to maximize or to minimize certain things. So if it is related to cost, in certain applications, we wanted to reduce the cost. In certain applications, if it is a profit-related cost, we wanted to maximize this. So the objective of any application, so the ultimate aim will be for either maximizing something or minimizing something. Suppose if it is effort, with minimum effort, what could be done? Suppose if it is time, with minimum time, what could be done? So this is where the optimization problem comes in. So this is where the intelligent devices should take up some kind of learning. It acts smartly, intelligently to minimize the cost and maximize the profit, or minimize the time and maximize the accuracy or efficiency, something like that. It will be always a trade-off between the maximization and minimization. So that's where all these optimization problems will come. So what is actually differentiable target function? So there will be a target function where this maximization, minimization will focus upon. So what is a differentiable target function? So the algorithms which are used will have derivative information. So it will go for first order or second order, some kind of derivations. And some algorithms, they do not have derivative information. So that kind of target functions will be used here in as an objective function here. So normally the classical algorithms use the first and sometimes even second derivative of the objective function. And other algorithms which are designed like direct search or stochastic algorithms, they are designed in such a way that the objective functions will not have function derivatives at all because they will not be available. So we have several techniques like exhaustive search, gradient descent, genetic algorithms, there are so many techniques available which can be used for optimizing the hyperparameters. Exhaustive search is a brute force search kind of thing, which will look into the most optimal hyperparameter by searching the entire search space. So entire population will be searched from top to bottom or from bottom to top, and it will find out which will be the optimal hyperparameter. So it is a brute force method normally used. Okay, they will not have any strategy at all. The strategy is just searching from top to bottom or bottom to top. And next is gradient descent. This is very most common algorithm for optimization for minimizing the error, and it will have an iteration over the training data set while readjusting the model. So the model should be readjusted again and again, and the entire data set will be readjusted. So over the training, it will go for again and again with so many iterations. And next is genetic algorithms. Genetic algorithms, it represent an attempt to apply the theory of evolution to machine learning. In the evolution theory, only those specimens will be surviving, and the survived specimens will reproduce, and it will have best adaptation mechanism. So the particles or the elements which can able to, or the specimens which can able to survive, will reproduce and will have the best adaptation mechanism. So this is how the genetic algorithm will work as in a human being or any other living organisms. So in the picture, you can understand the optimization algorithms. It actually have exhaustive explorations. So it explores into the entire population and finds out the optimum solution. And genetic algorithm and simulated annealing, they will have reproduction mechanisms which will adapt to best mechanism for reproduction, and we have gradient descent, and that will actually go for iterative kind of thing. So as given in the genetic algorithms, you can see create some random specimen and mutate some randomly, breed a new generation and find the best specimen from that. If it's not possible, again mutate something randomly, and it will go on like that till it finds out the optimum one. So this is how it will go in genetic algorithm. So the problems normally which comes with this optimization is the challenges, or it will have two kinds of thing called minima, local minima and global minima. So there will be many local minima and there will be one global minima. So sometimes the problem is the entire algorithm will stuck into local minima, thinking that it is global minima. Or even if it is having local minima, it will choose one local minima. There may be several local minima, but it will actually stuck into a local minima which is not actually optimum. So that is one problem. Another problem is, see, in the second one image, you can understand that. So there are so many solutions. So this is one solution, this is another solution, this is another one, and this is one. So it will change its learning path from here to here, then from here to here, then it goes on like that, which will take up a large time, or the rate of learning will be huge. But if the learning is like this, okay, it starts from here, learns to move, which is very near to that, and learns from here to move, which is nearest solution, like that. If it goes on learning like this, the learning rate will be very, very less. So these are some of the challenges which the optimization or improvisation of algorithms should take care of. The algorithms normally use derivative information like bracketing algorithms, local descent algorithms, first order algorithms, and second order algorithms. These are some of the kind of algorithms which will uses the first order kind of, derivations for its target function. The bracketed algorithms are intended for optimization problem with one input variable where the optima is known to exist within a specific range. So this bracketing, from the name itself, we can understand that there will be a bracket and a range of values will be given. So the optima is known to exist inside the range, inside the given range. And the algorithm will efficiently navigate in the entire range and locate the optima. Okay, but only single optima will be assumed here. Okay, so it is always referred as unimodal objective function. And some of the examples are Fibonacci series, search, golden section search, and bisection method. And next kind of algorithm is local descent algorithm. So it is intended for optimization problems with more than one input variable and a single global optima. So again, this is a unimodal objective function because it is going to have only one global optima, and more than one input variable will be considered here. Most common example of this local descent algorithm is line search algorithm. Choosing a direction to move in the search space, then performing a bracket. So it will choose first the direction, and in that particular direction, it will choose one range of value. That is, it will perform the bracketing type of search in a line or hyperplane in the chosen direction. So in one direction, so the local descent algorithm, it chooses the directions. Then in that, it will bracket a range of solutions. It will move on to each and every solution to find out the optimum one. And this process will be repeated again and again until no further improvements can be made. So until it becomes static, it will be going on doing all the iterations. The limitation with this algorithm is it is very, very expensive because it is going on iteratively. It is the computational cost is very high to optimize each directional move in the search space. Next is first order algorithm. This one uses the derivation, first order derivation. So first derivative is done to choose the direction to move in the search space. So this one will find out the direction by means of the first derivative, that is a gradient. And it involves calculating the gradient of the function, then following the gradient in the opposite direction. So using the step size. So the step size will be the learning rate. So if the step size is lesser, the learning rate will also be lesser. So it will find out the gradient of the function moves in the opposite direction to that using the step size. And this step size, it actually controls the movement of the movement in the search space. So how far it can search or how far it can move to the next optimum solution. And if it is too small, there is a problem with the step size being small. If it is too small, it takes long time and can get stuck. If it is too large, then it will result in zigzagging and bouncing around the search space, missing the optima completely. So there are two problems. So always the step size should be a moderate. It should not be too large, or it should not be too small. And the first order algorithms are gradient descent, momentum, AdaGrad, misprop, and Adam. So these are some of the kind of first order algorithms which uses the first derivatives. And second order algorithms, they are otherwise called as Hessian algorithms. It chooses the direction to move in the search space, and they are appropriate for those objective functions where the Hessian matrix can be calculated or approximated. So these algorithms will be used where the Hessian matrix can be calculated. So examples of this second order optimization algorithms for univariate objectives are Newton's method and second method. And for multivariate objective functions are quasi-Newton method. There are many quasi-Newton methods and are typically named for the developers of the algorithm like Davidson-Fletcher, Broyden-Fletcher, and limited memory BFGS. So these are some of the quasi-Newton algorithms. And as mentioned in my first slide, there are non-differential objective functions also, which will not take up the derivatives. So which will not consider derivatives because they may not have the derivative, they are not known of the derivatives, or they may not have much knowledge about the derivatives, or the derivatives may not be calculated. It's not possible for calculating the derivatives for certain algorithms. So those are called as non-derivative differential objective functions. So some difficulties in objective functions for the classical algorithms are no analytic description of the function is available, and they ends with multiple global optima. And they may have noisy data so that the stochastic function evaluation has to be done. And they may be discontinuous objective function. The regions with invalid solutions may be available. And because of that, discontinuity may be available. So these are some of the difficulties with the objective functions. So where we have the black box optimization algorithms, as they assume little or nothing about the objective. The black box optimization algorithms, they will not know anything. Either they will not know anything about the objective function, or they will know very, very little about the objective function. So such algorithms are direct algorithms, stochastic algorithms, and population algorithms. The direct algorithms are objective or functions which have objective functions for which derivatives cannot be calculated, and they are deterministic in procedures and often assume the objective function as a single global optima. They are unimodal, and it is also referred as pattern search. And some of the algorithms are cyclic coordinate search, Powell's method, Hooke-Jeeves method, and an elder simplex search method. Stochastic algorithms that make use of randomness in the search procedure, and derivatives cannot be again calculated, and typically involve a lot more sampling of the objective functions. But they will be able to handle the problems with the deceptive local optima. Some of the examples are simulated annealing, evolution strategy, cross entropy, and cross entropy method. Then the very popular and very simple, it's like a very simple and also very popular algorithm are population algorithms. This population optimization algorithms are stochastic optimization algorithms which maintain a pool of candidate solutions. So they will have a pool of candidate solutions that together, and these pool of optimums are used as a sample itself, explore, and hone in and one optima. So there will be multiple solutions. They will put all the multiple solutions will be treated as a candidates in the population, and one single, they will be moving together, or they will be together, and from that one optimum solution will be considered. And algorithm of this type are more challenging, that may have noisy function also, and many global optima multimodal. And among that, it will find out one good enough solution, which is either the good solution or good enough solution. That means near to the good solution. So like that, it will choose one thing. This pool of candidate solutions, they add robustness to the search, increasing the likelihood of overcoming the local optima. And some of the examples are genetic algorithms, differential evolution, and particle swarm optimization. So these optimization algorithms are very, very popular. These population-based algorithms are very, very popular. And most of the intelligent devices, they use such kind of population algorithm. And that's why I have taken in my keynote address to actually to say something on the population algorithm, how it actually improves the learning nature of the intelligent devices. So when it comes to optimization, selecting a best element with regard to some criteria from some set of available alternatives. So what is optimum means? There will be solutions, of course, and there will be alternate solutions also. Which will be the best one? Which solution is the best one? That kind of selection is called optimization. And it consists of, as mentioned, the objective is to maximizing or minimizing something. So it considers this optimization also, it considers as its criteria maximizing or minimizing a real function by systematically choosing the input values from within an allowed set and computing the value of the function. So it will systematically choose the input variables from an allowed set and computes the value of the function. After that, it finds the best available values of some objective function given a defined domain. That is, it will look into the constraints also. It will consider the constraints or the conditions also, or maybe rules also. Okay, for what will be the rule for maximizing or minimizing. And it includes a variety of different types of objective function, different types of domains. So there are so many objective functions are available. One for unimodal, one for multimodal, one for one objective, single objective, another for multi-objective, differentiable, non-differentiable. So many kind of objective functions are available, which can be actually treated as benchmarks for doing such kind of optimizations. Okay, so in any optimization algorithm, all those objective functions, according to the application or according to the data set, these objective functions can be used as a target function. So an optimization problem, it will be like this. So given a function from some set A to the real numbers. It will have a domain, which will be called as a search space here. Here may be the population. If you say population-based algorithm, the search space itself will be the population first. Then elements of A are called candidate solutions. So the population will have all the candidate or feasible solutions. So this will be given. So the solutions, candidate solutions or feasible solutions are known to us, and the entire thing will be called as a search space, which is nothing but the population here. And what it sort means, it has to find out one element X such that after applying the function f of x 0, O should be less than or equal to f of x for minimization, and f of xo should be greater than or equal to f of x in the case of maximization. So this function f is called as objective function. So the objective is to find out the minimum or to find out the maximum. So efficacy or accuracy or efficiency should be maximized. So the objective function, it talks about maximization in that case. Suppose if it is cost or time or energy, it should be minimum. So in that case, it will talk, the f of xo less than or equal to f of x should be used. So this is how the objective function will go. So if it is utility function or fitness function, it should be maximization. So all these things, it will talk about the objective of what we wanted to do. So multi-objective means there can be only one objective, it is uni-objective, simple objective function. More than one means it can have multiple objectives and it will be optimized simultaneously. So more than one objective will be there in multi-objective and it will be optimized simultaneously. There will be trade-off. For example, in a knapsack problem, so we have to make use of the sack which is given. At the same time, we have to put in many, the number of things you are putting into that should be maximum. So minimum, at the same time maximum. So that will be multi-objective things. Multi-model optimization is one clear solution will be there, which is unimodal. And more than one mean, we have to consider it as optimum, then it should be multimodal. So computational optimization techniques normally terminates either in one finite number of steps. So we have to give them this many number of steps you have to go and you have to stop. So in a finite number of steps, the algorithm will stop. Otherwise, if you're going to take it as an iterative method, till it converges to a solution, the iteration will go on to loop. And sometimes there will be heuristics, which will provide, this will be the approximate solution. For example, suppose I'm fixing up minimization of error. Okay. So if it is MSE, then the error should be minimum and it should be near to 0. It will not become 0 at all, but it can be near to 0. So when it reaches near to 0, I can stop. So that is the heuristic that provide approximate solution to some problem. So the iterates may not converge to 0 in the case of MSE. It may not converge to 0, but it may converge something near to 0. So we can take it as, okay, we have come for an approximate solution. So these are some of the points where the algorithm will try to terminate or where the algorithm should terminate. So the iterative methods used to solve problems or of nonlinear program differs according to whether they evaluate Hessians or gradients or any other function values. And this actually improves the rate of convergence. So if you take Hessians or gradients or any other function values, it will actually improve the rate of convergence. But there are certain problems also which increases the computational complexity or computational cost because it has to iterate many times and the learning rate may be huge when it moves from one space to another. If the space between, the step size is between one solution to another is huge, then the computational cost will be more. So when we look into such kind of optimization algorithm, we have to see whether the computational cost is increasing or not. That also we have to consider. Many heuristic algorithms are there: mimetic algorithm, differential, evolutionary algorithm, dynamic relaxation, hill climbing with random restart. All these are certain kind of heuristic algorithms. Now coming to population-based optimization, as I mentioned, I have actually chosen one particular population-based optimization, which we derived as a team. We derived this one from the nature-inspired or bio-inspired computing paradigm. So this population-based optimization, it's when you talk about the population-based, it consists of n particles, and each particle here we can take either particles or elements or whatever may be the population's element, and it will have a position. So every element will take up one position, and it will stand for the potential solution in the d-dimensional space. Given search space, it will take up one position and it will be treated as one potential solution. So they are all candidates. And these elements will change its condition according to the following three principles. To keep its inertia, so it takes some kind of energy, okay? And it changes the condition according to the most optimist position. Suppose if it thinks that either another position is optimum, then it will move from that position to the next position. And it will change the condition according to the population's most optimistic position. So it will actually takes first, it will consider its own position. It will try to improve its position. It will change its condition according to, suppose if I have the cost of 10 rupees at a time, and if I think that I can do that for 9 rupees or $9, so the optimum thing is, if the objective is to minimize the cost, then $9 will be the optimum. So I will try to do that for $9. So that is the second one. And the third one, some other solution is available there for $8. I have taken my own thing as optimum as $9, while another optimum solution is there for $8. Then I will go for $8, which is optimum, population's most optimum. Okay, among all the optimum solution, 8 is best. So in that way, it will take up the energy first of all, and then the optimum solution by itself, and the optimum solution with the nearest solutions. So like that, it will consider 3 things among itself. So there are certain basic parameters for this population kind of algorithms. The population size, the number of elements which are present in the population. Okay, and if there are more elements, the diversity will be more. And the neighborhood size, suppose if one solution is there, who will be the neighbors? So the neighborhood size defines the extent of social interaction within the population. So there will be this population kind of algorithms. The elements will actually collaborate, coordinate among themselves. There will be some communication between each other. So that social interaction will be there. So this neighborhood size actually defines the extent of social interaction within the population. So the smaller the neighborhood, the interaction will be less. And then the number of iterations. So to reach a good solution, how many number of iteration it has to go? It depends on the problem. Suppose if it is too few iterations, it will terminate the search prematurely. So the search will end even without getting the global optima. It may stuck into local optima. If it is too large number of iterations, the consequences of unnecessary adding up the complexity, computational cost will be there. So the iterations will be actually initialized or actually selected by the programmer in such a way that the termination should not be premature, or it should not bring any complexity into the computing. And then next parameter is acceleration coefficient. It can be random, which controls the influence of the cognitive or social components on the overall velocity of the element. Velocity means if it is a moving element, then the velocity. So the terminologies may be different. Every population algorithm will uses its terminology in a different way. So this is a small population algorithm, which is of population-based algorithm. This I have taken from the PSO to explain what it is actually. So in the particle swarm optimization algorithm, it is like particles moving in a group, like a bird flocking. Okay, the particles are nothing but birds here, and swarm means grouping. So the swarms, they will move in a group to attain a particular place. Okay, so in that case, one particular bird will be moving in the front while the other will follow. So the inertia, the strength, or the the inertia taken by the first bird will not be for the second or the third one. They will be moving with less inertia. Okay, and they will be moving in one direction. And after some time, among the neighbors, they will adjust themselves. Like that, they will adjust and adjust so that they can move for a very long distance. And finally, they will reach for the solution. So there will be some collaboration, some movement, and also the direction is very important. So how it goes means the initialization of elements with random position will take place. So random position and random velocity, they will start moving. And for each element, the position will be evaluated with its fitness. So if fitness is better than the fitness of one cell, then the better fitness will be taken care. This will happen among the particles till the particles or still the birds exhaust. And again, it will start with the neighbors. So first it will find out it will evaluate its own fitness, and it will take up the best fitness among itself. And then it will start with the neighbors. It will go to the G base, the neighbors based, and they will change the positions. So it will iterate and iterate again till it reaches the particular optimum solution. So the G based will give the optimum solution. This is how normally the PSO will work. So this is very similar to all the population algorithms. This is the one which is very simple to understand. So each particle, here it is each element, and it has a fitness value, that is the objective function, and it will have a velocity for flighting, and it will have two current based. One is the best solution it has achieved so far, and the best solution any element has achieved so far, which is comparing with the neighbors. And this element tries to modify its position, either the current position and the current velocity, and also it will take care of the distance between the current position and the p-based, distance between the current position and the g-based. So the step size will be the distance between the current position and the p-based. So by itself, what will be the distance? How much it has to spend? How much velocity it has to change? The position may be changed because it is going to actually compare with its own velocity. So how much distance gap will be there for adjusting its own velocity to become the p-based, and the distance between the current position and the neighbor one, which is having a optimum velocity. So like that, it will compare and it will try to modify its position and also the velocity. And each element in this population, it keeps track of its coordinate in the solution space, which are associated with the best solution it has achieved. And under best value, it is tracked is the best value obtained so far by any element in the neighborhood. Okay, so like that, it will goes between G-based and the P-based. And the stopping criteria will be, it terminates when a maximum number of iterations has been exceeded, terminate when an acceptable solution has been found, terminate when no improvement is there. Suppose if it becomes stable for a particular time, everything becomes stable, so it will stop. So no improvement is observed at all. And terminate when the normalized population radius is close to zero. Suppose if it has moved from one place to another, it actually searched through the entire population and the radius is very close to zero, then there is no meaning of actually learning. So it will stop and terminate when the objective function slope is approximately 0. So the function slope is approximately 0 also, it will terminate. So there are many objective functions which can be categorized as continuous, discontinuous, linear, nonlinear, convex, non. So we can categorize all the objective functions, and some of the functions are Oakley, Adjiman, Alpine, Beal, Prana, step functions. So I have given the categorization also inside the thing. So according to the application or according to the data set, according to the problem, you can choose such kind of benchmark test functions for your optimization. Now coming to the problem, where we have applied this kind of population algorithm and what kind of population algorithm we have actually designed. So this is the case study which I am going to show you now. So we have the World Health Organization. It states that approximately 285 million people are visually impaired in the worldwide. And among the individuals, 39 million are affected by total blindness. So navigation is very, very essential for any human being. And if it is total blindness, you can think over the difficulty that arises for navigation. So 39 million are affected by total blindness and 246 million people have low vision problem. So for human assistant, we actually designed a small supporting device, and we tried to imbibe some kind of intelligence into that for safe mobility, location identification, which are two primary challenges normally faced by these visually challenged people. So the objective is to actually design an affordable, reliable, robust, and intelligence-based assistive device for the blind person for object detection and obstacle avoidance during the navigation. So the purpose is actually to test our optimization algorithm also, which is named as synergistic fibroblast optimization. And we have the classical Q-learning algorithm. So along with the optimization, synergistic fibroblast optimization, how this classical Q-learning algorithm is performing. That is the objective here. So the secondary objective is SFO optimized Q-learning approach embedded on microcontroller integrated sensors is proposed. And we designed and developed a walking stick, which improves the safe mobility of visually impaired people in private and public places and to empower them self-sustainability in the living environment. So when it comes to Q-learning algorithm, it is one kind of reinforcement learning where we have all these time we are talking about machine learning, artificial intelligence, all these things. So reinforcement learning, it deals with intelligent agents which acquires the knowledge through learning and performs actions on the environment. So it's a kind of agent which actually takes up the knowledge through learning. And it attempts to learn the control policies and tries to maximize the cumulative reward function value using the dynamic interaction with the external world. So there will be certain kind of control policies and it tries to maximize the cumulative reward function. So this learning mechanism, so if like a child, if it learns, if you try to give some reward to that, then the child will actually feel happy to learn more and more. Like that, there will be a reward function and also a penalty. So this reward function is considered here. The reinforcement learning always tries to maximize the reward function value. And the most widely used RL algorithm is Q-learning algorithm, which learns and performs actions in particular states. So there will be states here. The construction of state action space transition matrix is mapping a set of continuous state into discrete action problem. So the limitations of this Q-learning algorithms are the Q values will be stored in the Q table, and the possible number of states and possible number of actions for each state are constructed in this Q table when the dimensionality of Q table gets increases. So we have the states and the actions. So if there are more states and more actions, the learning gets affected. So the convergence behavior of this algorithm, the Q-learning algorithm, gets affected in finding out the optimal value. So there is a limitation here. So what kind of solution we have given? By using the synergistic fibroblast optimization algorithm, it is actually made the Q-learning algorithm to choose optimal rules for the construction of Q table. So instead of going for bringing in the optimal solution into the population, we actually given optimal rules into the population in the construction of Q table. So which rule will be optimum? If we use this rule, this will become optimal rule, and this will give you an optimal solution. In that way, we made the intelligent device to design the entire thing with optimal rule by choosing the optimal rules. So it is applied to choose optimal state action space in Q table with an objective to maximize the cumulative reward function value and convergence rate into Q table, which can significantly improve the learning process of the classical Q learning algorithm. So it is formulated to develop the optimal path finding scheme that improves the learning ability of the walking stick for solving object reduction, location identification, and obstacle avoidance. So it is this synergistic fibroblast optimization is a population-based global search algorithm that imitates the behavior of fibroblast organism. This organism is a microorganism which is normally present in our body. This organism is actually, it moves with its strength called collagen, and when it moves, there are so many cells, such kind of cells will be available. They will move towards a wounded region, and it makes the wounded region to heal faster. Okay, so that inspired by the mechanism of such kind of fibroblast organism, we developed this algorithm. So it is to find the maximum or minimum, which is an optimal solution to solve a non-linear complex problem. And they have various characteristics like migration, moving from one place to another, reorientation, orienting towards something, and alignment, aligning towards its own neighbor, ECM synthesis to develop its own collagen. They are collaborative, they are goal-oriented, they will interact with each other, they will regenerate, self-adapt, and evolution. So many things are there. Actually, this particular organism has so many things which actually does some magic in our body when we are really wounded. To heal the wounds, this kind of magical microorganism is used. So this is how it looks. Here we have a population here, and we will see which solution. These are solutions, candidate solutions, and fitness will be tested, and according to the fitness, it will be reoriented, and according to the neighborhood, the updation of velocity and position will be changed. It will take up the collagen actually. According to the collagens, best collagen will be taken at its velocity and also the position, and it will go into the ECM synthesis. If it is okay, it will come here. Otherwise, optimum solution will be chosen. Otherwise, it will go again and again till it reaches the stopping criteria. Okay. So this is the proposed work. So we have the learning environment, and we have so many rules. Like if there is, we have actually placed with sensors like ultrasonic sensor, color sensor, PIR sensor, proximity, and even the pit sensor, so many other sensors. For 5 or 6 sensors we actually put, and we have put all the rules like ultrasonic. If there is an obstacle in 10 meters, it has to give, there will be a rule. And if it can turn either this way or that way. Even if you turn like this, it will check for the proximity and also the obstacle, and it will see the sensor. All the sensors are actually connected, and GPS and GSM to find out the location is here, and solar power, it is connected with solar power. This is a stick here. So there are, because of all these 6 or 7 sensors, we have so many rules, and this device should take up which rule to make it possible, the optimum movement to find out the obstacle. Okay, so the rule policy derivation and rule set are there in the learning environment. Okay, using Q learning algorithm, we have taken up all the rule set. Now the UCM with the Q values are given. So this is this whole thing is about the optimized Q learning. Stochastic selection of Q values chosen by the fibroblast and reward function will be taken, and optimized rule set will be given into this OQ1, OQ2, everything. And using this optimized rule, the knowledge representation based on the optimized learning rule will be given to the intelligent device. So the intelligent device, it acts with a intelligent learning mechanism. So that is the kind of proposed methodology or approach we use for this device. So this is the algorithm. I'm just skipping this algorithm. Instead of that, I will explain. This is the aerial view of our university, and we have taken for movement, we have taken this one, this green one, because you can see here, there is a cross here, it has to take this turn, and there is three-way here, but it has to move this way and this way. There is again an obstacle here. There is a chance of obstacle here, people coming over this way, and when this person moves here, there is this way, and this way, they have to move. So like that, we have taken this one for training and this one for testing, the blue one for testing. So this is the, when we take the ultrasonic detection distances, see here, the actual distance is in blue color. The all the sensors, whether it's going good or not, we verified with all the sensors. So distances are calculated, and it's not much differences are there. And this is for motion detection versus PAR detection, whether the PAR sensor could able to actually detect. So we have taken, so this is actual, blue one is actual, and the red one is the PAR sensors motion detection. So not much difference. We tested with all the sensors first. And then this is ultrasonic distances. So this is one, ultrasonic distance is residual, and this is for PAR detection. So the residual also we tested. And now coming to the parameters, the learning rate of, we tested with other population-based algorithms like cuckoo search, differential evolution, and PSO, and this SFO. The learning rate of C classical Q learning is alpha is 0.3, while population size for SFO is 10. This is state minus action space, and this is also state minus action space. And but we have set SFO's population size as only 10, and the discount factor for classical Q learning is 0.5, while we have set the iterations as 1000 for all the other population-based algorithms. And Q table will have state minus action space, while the dimension of SFO is 10, PSO is n, D is n, and cuckoo search as n. And the coefficients are set like this. ECM is set to Q table, state minus action space. And with these parameters, we tried the learning mechanism or learning rate of the intelligent device. So the fitness evaluation of algorithm. So if you say,
excuse me, Professor, can you conclude, please?
Sorry?
Can you conclude, please?
Yeah, 1 second.
Okay.
So this evaluation of the algorithm, SQL with SFO, it is good. And also for performance of evaluation of the algorithm, the classical Q learning and SFO seems to be good. So when you see this table, you can understand the number of learning rules which are used for each kind of approach. For classical Q learning, it was 92, while classical Q learning plus SFO, because SFO actually defined the learning rules, it used only 17, while PSO used 24, D used 32, and cuckoo search used 39. So when compared with all the other population algorithms, the learning rules, optimum learning rules selected by SFO is only 17, which actually made the intelligent device to learn very fastly. So the success rate is, for this kind of object detection is 94, for motion detection is 89, and for light detection is 100. In the top of the walking stick also there is a sensor, it is 75, and for GPS embedded walking stick it is 100%. So this is what the proposed model, it gave the success rate. So finally, as a conclusion, I actually told you what is actually demonstrated one case study where the population based optimization algorithm can be used for reinforcement learning or improvised learning in the intelligent devices. So this work is supported by one of the project under the government of India. So I have to acknowledge that. These are some of the references. So thank you so much. And if any queries are there, you're welcome.
Okay, thank you very much for this nice talk with many issues and many knowledge, many results. So thank you very much. I think you have, maybe we can go to the chat. We have two questions. Can you read this question, Professor?
Yeah, in the chat. Okay, okay.
Yeah, in the chat, yeah. What are the hyperparameters used in the case studies? The first question.
Okay, those are the rules actually. The hyperparameters used here are the various rules which have been actually defined for PSO. It is 92. There were 92 rules, and those parameters are set actually. The rules are set actually. So that's the first question. And how to choose why these parameters? Actually, these parameters, they're the focus. We are focusing on the hyperparameters, like all these rules, how to reduce that. So those are the parameters. So we have to actually talk about that. Okay.
Okay.
Yeah.
Another question?
Why? What is that?
Okay. Yeah, I'm just asking the audience if they have some question, other question. May I have one question now about the scalability issues of the proposed algorithms?
Sorry?
What is the, I mean, I would like to know about the scalability of the proposed algorithms.
What? I couldn't understand.
The scalability. I will write it.
Yeah, please.
When we deal with the civil. Yeah, I just write my question.
Scalability, yeah, of course. The proposed algorithm. You can use for any real-time data or time series data. We have applied the same kind of optimization algorithm for a data where we have big data. The velocity and the veracity of the data is big, time series data. So it is scalability. There is no issue in scalability for population-based algorithms. It works with any kind of scalability. You can even use it for, because the solutions, it may range for anything. The data can be scalable. We will be choosing the solutions from all the candidate solution. It works, of course. The scalability issue is not there.
Okay. Maybe we have another question in the chat. But I would like to know how to apply non-differential loss function in the case of neural network.
How to apply non-differential loss functions in the case of neural networks, which domain function because of the backpropagation. In the case of neural networks, so actually in the case of neural networks, we are not actually using neural networks here, but we can go in for optimization algorithms into the neural networks. So by finding out the weights and all, the weights or bias, we can apply optimization in choosing up the weights or choosing up the bias in the neural network so that it may become the loss of neural networks or such kind of objective function can be reduced. Yeah.
Okay, thank you very much. If we don't have the question, thank you very much, Professor, for this nice talk. And I will give the floor to Professor Haqiqi, please.
Yeah. Thank you so much, Professor Lajel, to chair these first keynote speakers. And thank you so much, Professor Subashini, for your nice presentation. And thank you so much for accepting our invitation.
Thank you, sir. Thank you so much.
Keep safe, please. We keep in touch. And
yeah, please.
Thank you so much. And now we move to the first session on the deep learning and IoT. And I asked Professor Brahim Orbi from Moray Islamic University, Makinas Morocco, to share the first presentation. And after, Professor Lavika Joel from Malivia National Institute of Technology, India, will share the sixth last presentation. Professor Brahim, you have the floor, please.
Thanks, Professor Abdul Karim, for your talk, and nice to meet everyone and to chair this session. First, thanks for the organizers for giving us this opportunity to share our knowledge and experiences. I will chair this session with Professor Lavika from National of Technology, Jaipur, India. Each presentation will take approximately 10 minutes. Please put your questions in the chat box. So we can move to the first presentation.
Good afternoon, sir. Good afternoon, all everybody.
Yeah, Lavika, you want to tell us some things?
No, sir. I was just saying, I was just wishing everyone good morning. It's morning in Morocco. It's afternoon here in India.
Yeah, sure. Thank you so much. Thank you so much.
Thank you so much. Nice.
We can,
nice.
Yeah. Thank you. We can begin our presentations.
Okay.
Thank you, Professor Lavika. The first speaker is Jaydeep Singh Sajiv from India, I think. It is about deep learning models using auxiliary classifier GAN for COVID-19 detection, a comparative study. Please, you have the floor. Are you here, please? Nitu Badangar, or Rohit Bantgar.
Brahim, you can move to the second one. If the first one is not here now, you can move to the second one.
Yeah, thanks, Professor Abdul. The second presentation is there in one of the authors here? I think Khawla Ishabi. Are you here, please? Do you hear me? Khawla. Mukhtar Zamouri. Do you hear me, please? So let's move to the third one. Hadir Al-Sa'dawi, are you here? Hadir? Hadir, are you here? Are you with us? Khawla Shabi, the second. So let's move to the fourth one, Yahya Bouktib. Yahya?
Yes, thank you.
You have the floor, please.
Yes, thank you. I will share my Assalamu alaikum. Hi everyone. My name is Yahya Bukhtar. I am a PhD student at LM2I Laboratory in the National Higher School of Art Crafts in Samix, in Morocco. I'm very happy to put our work titled a deep autoencoder-based multi-criteria recommender system in this conference. This was prepared by me, Yahya Bukhtar, and my dear professors, Mr. Ibrahim Wahbi and Bushra Frikh and Mukhtar Zammouri. First, let's talk about the outlines. With a short introduction to multi-criteria recommender system, then discuss our proposed method where we give method of calculation of criteria weights and the architecture of our deep autoencoder. After we move to the experimental studies, and finally the conclusion and future work. As you know, traditional recommender systems try to quantify the user preferences about items using a numerical value called rating. Since the use of recommender system has been increased, user expectations have been differentiated. User may judge items according to different criteria. This gives birth to multi-criteria recommender system. Therefore, additional information dealt by multi-criteria ratings can help enhance the recommendation performance by accurately modeling the user preferences. For example, we can easily imagine assigning different rating to a restaurant expressing how much we liked the food, the decoration, and the service. Such multiple rating could be exploited by a recommender system in order to identify more effectively which items should be suggested. Users provide the rating on multiple aspects of an item in a new dimension, thereby increasing the size of the rating matrix, of course, and this will open up some challenges for researchers in particular. We talk about two problems: data sparsity and the calculation of criteria weights or the attributes weights. In the paper, we propose a multi-criteria recommender system model based on two things. First one is a deep neural network, or a deep autoencoder to learn high-order features and to generalize better to answer feature combinations through a low-dimensional dense embedding. This will be a good solution for high-dimensional and sparsity problems, of course. And our model is based also on a multi-criteria decision-making method, which proposes a correlation coefficient and standard deviation, or called the CSD, integrated approach to determine the weight of each criterion. So first we compute the overall rating prediction for each item using the CSD integrated approach. Then we train our deep autoencoder with the calculated rating to predict the missing values. To calculate the criteria weights or the attributes weights, let's be n users from user 1 to user n who have rated m items based on key criteria. We compute the criteria weights with the CSD method as follows. First, we relate the person's correlation coefficient RG between the values of each criterion CG and the overall rating R0, as mentioned in equation 1. Sorry. Then the attribute weight WG is computed as in equation number 2, where sigma G is the standard deviation. Let's talk now about our
Yahya.
Yes.
We don't see your presentation.
Oh, sorry. I will reshare it again. Wait. I will share it. Now?
Yes, okay. Yeah.
It's okay now, yeah.
Sorry. So, as I said, the attributes WG is computed as in equation number 2, where sigma G is the standard deviation calculated as in equation number 3. Let's talk now about our deep autoencoder. As a definition, we can see that a simple autoencoder is just a neural network that implements two transformations, an encoder and decoder. In the encoder stage, we just map the input X from a dimension D into a low dimensional encoding Z, where D prime, the dimension of the low dimensional encode, is smaller than the dimension of the input. This late presentation is then mapped back to a reconstructed vector X prime that has the same dimension as the input. We discuss the detail of the architecture of our deep autoencoder in the experimental study sections. A deep autoencoder is just an autoencoder with more hidden layers. First, let's talk about our datasets. So we use Mobilance 100K datasets, which is a stable benchmark dataset containing 100K 1K users and 1.7K movies. The problem here is that Mobilance is a single criterion dataset, so we had to convert it to multi-criteria Mobilance 100 by randomly generating two criteria ratings on a scale of 1 to 5 for each user. In deep learning algorithm, choosing the right activation function is very crucial and important. Therefore, we conducted some experiment. Note here that we only compared the note here that we only compared the most used activation function.
إذا كنت راه لا سيسيون إلي اون كور يعني نقدر نقول
please مختار. Yeah, Yahya, you can continue.
Yes, note here that we only compare the most used activation function, the ReLU and ELU. According to the result, ReLU got better results with deep networks. Therefore, we take as an activation function in the hidden layer. To explore the effect of number of hidden layers, we conducted some experiments. Table 2 show the results. we got the best results with deep networks, 5 hidden layers. Model number 3. However, the model starts to overfit with 7 hidden layers. Thus, we take the 5 hidden layers model as our autoencoder, the model number 3. Top 3 shows the comparison of the proposed method with other models, like the SCDAA, or what we call single criterion deep autoencoder model. MC1 deep autoencoder is a multi-criteria deep autoencoder that use only the first criterion, the overall rating. MC2 deep autoencoder is multi-criteria deep autoencoder using the second criterion and the overall rating. And MC deep autoencoder is a multi-criteria deep autoencoder using the average of all criteria ratings as an overall rating. According to the results, we can see that all multi-criteria based models outperform the single criterion model, first one, let's say the deep autoencoder. Furthermore, the proposed approach outperformed all the other methods. We got the lowest root mean squared error and MAE. MC1, we can notice here that MC1 deep autoencoder performed better compared to MC2, which means that the first criterion is more important to users than the second one. We can conclude that our CCSD-based method of computing the criteria weights has enhanced the accuracy of proposed deep autoencoder-based multi-criteria recommender system. As a conclusion, we demonstrated in this paper that the multiple criteria rating methods can outperform easily the traditional ones, such as single criterion recommender system that considers just the overall rating. And extracting relation between the different criteria ratings is the key for enhancing the recommendation accuracy. Therefore, we posed CSD method for calculation the attributes weights. Furthermore, a deep autoencoder was proposed to deal with data sparsity and high dimensional problems. As a future study, we plan to conduct experiences on multi-criteria datasets like TripAdvisor MC and the Yahoo Movies datasets, and to compare our approach against more multi-criteria methods. Thank you.
Okay, thank you, Yahya, for your presentation. Questions, please. Yahya?
Yes.
Hear me? Can you read on the chat box? One question. I want to know how the ground truth used for the evaluation in the movie dataset is made up. Thanks.
So as I mentioned before, we used the movie lens datasets and we converted to a multi-criteria by generating two more criteria rating. Generation was randomly made and on the scale of 1 to 5 rating scale. After computing with the CCSD, after computing the criteria weights, we feed the computed weights to our deep autoencoder network in the input, and we try to reconstruct the missing values, the missing rating with the deep autoencoder.
Okay, thank you. There another question. or we can move to Professor Lavika. You have questions about this presentation? Since I am an author, I can't ask.
No, sir. Actually, somebody has written in the chat box. So if you see, if somebody wants to know how the ground truth used for the evaluation in the movie data set is made up. So that is the only question from the audience, nothing from my side.
Okay, thank you.
Yeah.
So for the next presentation, I'm asking if someone of the three previous talks are here. For the talk number 1, deep learning models using auxiliary classifier. Is one of the authors, are we with us? No one.
Ibrahim, please ask Mukhtar Zmouri if he is here.
His students will present in a few minutes.
Okay.
So what about talk 3, deep learning method for bone abnormality detection? Hadir Sa'dawi, Manal Tantawi. Okay, we move to the number 5, COVID-9 X-ray model detection using convolutional neural network. Mushira Ghalib. Or any one of authors of this talk. Hala. Okay. We move to the 6th one. Mayar Shafi'i.
Hello.
Yeah.
I'm Dr. Muhammad Salim, second author of this paper.
Oh, thank you for being with us. Please, you have the floor. You can give your presentation.
Okay, I will share it. Do you see my screen now?
Yeah, it's okay.
Yes, we can see your screen.
Sorry?
Yeah, we can see.
Okay. Hello everybody. I am Dr. Muhammad Salim, Associate Professor in Ain Shams University in Cairo on leave, and now I am Associate Professor in the German University in Cairo. I am happy to present the paper titled Review on Supervised and Unsupervised Deep Learning Techniques for Hyperspectral Images Classification. These are the outlines of my talk. First, we give a short introduction to the topic. Then I will describe the hyperspectral dataset that's used in this research. Then I will shortly introduce some of the conventional segmentation methods used for this problem. And then the main part of the talk about the comparison between supervised and unsupervised learning approaches. And finally, I will conclude. We all now have some experience with satellite images. We have it in different applications of our daily activities. Artificial satellite produce numerous scans known as remote sensing satellite images. These scans could be categorized into different, using different categories. One of these categories is the number of wavelengths captured or stored in the images. We have simple RGB images or multispectral images or hyperspectral images. A lot of work needs to be done on these images. One of this work is to segment the images to recognize for example, the purpose of the land use, or to detect the objects in many applications like for agriculture, for security, for monitoring, and so on. This image, in this slide, we see an example of a hyperspectral image. Hyperspectral image consists of tens or hundreds of different wavelengths. Every wavelength is stored in a spectrum for its own. Ranges from short wavelengths to long wavelengths. In this work, we discuss different approaches used to segment these images. Some of these approaches are based on supervised techniques, sample chain and techniques, and other approaches are based on unsupervised techniques, mainly autoencoders. We will also introduce table of the popular standard data sets used for testing, and we will also discuss what we mean mainly by supervised and unsupervised techniques in this topic. This is a table of the standard data sets available for testing. Some of these data sets are used for classification, pixel-wise classification. Some others are used for unmixing, and some others are used for different other problems. However, we are concerned with pixel-wise classification, so we are concerned with the first 8 data sets: Indian Bens, Salinas, Bavia C, Bavia University, Bavia City, and Bavia University, Kennedy Space Center, Washington, D.C. Mall, Botswana, Cook City, and all of these are used for pixel-wise classification. We see that the size of the images ranges from small images like in Indian Bens, 145 times 145, to high resolution spatial images like in Washington, D.C. Mall or in Botswana, where one dimension of the image, or the spatial dimensions of the image, exceeds 1K. One critical parameter in hyperspectral images is the number of spectral bands. It ranges from all of the available data sets are above 100 bands. Bavia City and Bavia University are almost 100 or a little bit more than 100. Then we have Indian Bens 200, Salinas 224, Washington DC is 191, and so on. Also, the data sets are different in the spatial resolution, which is ground resolution. So, for example, Bavia City and Bavia University have a ground resolution of 1.3 meters per pixel, and Botswana is very low resolution image presented by 30 meters per pixel. The number of classes is another challenge. As much as the classes, then the complexity of the proposed solutions or the complexity of the proposed solution is depending very much on the number of classes. We see here that Indian Bens and Salinas have 16 classes. However, there is a small version of Salinas called Salinas E, has only 6 classes. Then we have Bavia, have intermediate number of classes, 9 classes per image. This is sample of the data set. We see here Bavia city, and this is on the left is the image. It's not clear. Maybe it's a gray. It's appear here as a gray level image. However, it's a hyperspectral image. On the right is the ground truth of this image, where every class is represented by color, and the white color is representing the background. So we have classes, for example, for water, classes for urban, classes for streets, and so on. And this is another example called from Salinas, a small version of Salinas, Salinas A. It has only 6 classes, and we see on the right side is the ground truth of this image. As I said before, every class is represented by a color, and the objective of this of working with such images is to introduce a pixel-wise classification. So we need to give a label for each pixel independent on the others, and this label should be one of the available 6 labels in the ground truth. The conventional segmentation methods, some methods based on the gray level value of the pixels, so they don't concern with the depth or the multispectrum of the image, and they were used widely before, like maximum likelihood estimators and the Gaussian mixture model are used for this task, for the classification. Minimum distance to mean. This is a very simple and naive distance function, and the other distance function, this higher order distance functions. Some conventional techniques also used the spectral and spatial information, like where the pixels considered as long vectors independent of the neighborhoods and classified independently on the others. I mean, in this case, we consider the pixels as a one-dimensional signal, and we can utilize any one-dimensional classifier used for one-dimensional signals for this task. Some other approaches use spatial information together with the spectral information. So they consider, for example, a small region from the image and reshape this region either to form one-dimensional vector to be fitted, for example, for neural network, simple neural network, or to different other classifiers like SVM and so on. In our work, as we said, we introduce a comparison between supervised and unsupervised techniques. However, we limit our comparison to techniques based on the convolutional neural networks. So before, the conventional pipeline for pattern recognition was could be abstracted in these 4 steps. First, we have an input image, then we do some pre-processing like reshaping of the image or converting the image from color domain to another color domain, or reducing the size of the image, and so on. And then we go to the step of feature extraction. In this step, we try to extract the best powerful representative features, the features that can differentiate between 2 different samples from different classes, and find the similarity between 2 different samples in the same class. So the features are important to show the variability between the classes, but the similarity within the class. Then we go to the classification method, and a lot of classification techniques were proposed. However, with machine learning, we have now feedback from the outputs, we have a ground truth data, and we use this ground truth data to tune the classifier to best match the features that we extracted before. In this case, we call this supervised techniques, since the classifier produces an output and it learns if this output matches our expectations or not. If it matches, then everything is okay. If it doesn't, then we use a difference between the ground truth data and the result of the classification to update again the classification parameter in order to reach better results in the next iteration. And we go in these iterations until we reach a certain level of accepted error, or we leave to, or we reach a stable values of the parameters. However, with the deep learning techniques, we use the same approach, but not only to justify the parameters of the classifiers, but also to adjust the parameters of the feature extractions. So in this case, we use the feedback from the ground truth, or the difference between the ground truth data and the results of the classifier to update the parameters of the feature extractions. Mean that we are not now worry about how good our feature extractor, what the features that are extracted are meaningful or not, because we have the chance to update these features using a feedback from the outcomes of the pipeline, of the big pipeline. What we will do now, we will extract a huge number of features, and we will hope that the good features will survive and the other features will die. And at the end, we will get more representative features. However, they are still selected in an automatic way, not by feature extraction engine. It works very fine, and the results show that this approach is powerful and will give us better results than conventional machine learning techniques or the conventional pattern recognition technique. So now we have a neural network, and instead of having only an input layer and then classification layers, we have in the middle a set of layers, and these layers are, or the objective of these layers is to extract features. So we have now in one architecture feature extraction and classification. So this is a form of new architecture used in deep learning. If we are using convolutional neural networks, then we mean that we don't only use deep networks, but we use also neural networks that has one or more convolutional layers. Means that one or more layers do the task convolution instead of the task of the weighted sum, only the weighted sum of the answers. The first convolution neural network was introduced in 1998 called LeCon. However, it was not given a good implementation of this network, and it was very difficult to use this network in huge amount of data or high resolution images. In 2012, Alex and his colleagues proposed an GPU-based implementation for the convolutional neural network, and proposed a long architecture that could be used for image classification, for larger scale image classification. And since then, this implementation is used widely, and we have every year tens or hundreds of new models that are based on the work introduced in 2012. most of the available networks now are trained trained on a huge number of images. Most of them are trained on that data set called ImageNet. It has more than 15 million images and more than 20,000 classes. Such models like AlexNet, GoogleNet, ResNet, BGGNet, CafeNet, and so on. So what we mean by CNN or convolutional neural network is that a network that consists of multiple layers. Some of these layers are based on the convolution, and instead of having a fully connected layers, we have a receptive fields, which means that the neuron in the hidden layers can see only small part of the image, and the size of this part is determined by the size of the convolution filter used, and the position of the neuron represent or corresponds to the position of the image that will be seen for this neuron. And by this way, the number of learnable parameters have been dramatically reduced from thousands of parameters into few parameters per layer, maybe 50 or 90 or hundreds parameters, but not thousands as before. And by this way, it was possible to stack multiple layers in this way. At the end, we flatten the extracted features, called also activation map, in order to have one-dimensional vector of the features and feed these features to a feed-forward neural network for classification or any other classifier. So in this table, we show recent work used CNNs or new models based on CNNs like ResNet or AlexNet, and the results that achieved for pixel-wise classification. The best result was using ResNet in 2019, and the achieved result was 96.4. The citation, the correct citations of this work is better to found in the article. However, this is the title of each of these three papers. What we mean by unsupervised technique is the use, mainly the use of the auto.
Mohammed, could you please conclude?
Okay. I will need just 2 minutes. The second part is about autoencoders, and autoencoders we feed the system with the input, and we expect that from the network that it generates again the same input. However, we can, and what we gain the features representation in the middle of the autoencoder. It's called unsupervised techniques because we don't need labeled data. We need only the data in themselves, and we can train the network to produce the same data. However, we instead of that use labeled data, and we tell the autoencoder if you saw this image, then the correct scene of this image is a segmented image. That's why in this figure, for example, we have the input x1, however, the expected output is x1 head, which is a new version of the inputs. The first work we can represent here is used multi-scale autoencoders. We see that the feature vectors of multi-autoencoders are shared together and in different levels in order to achieve better results. Actually, results between 95 to 99% was achieved. The second work is representing multiple stacked autoencoders. So first of all, the hyperspectral image is reshaped into one-dimensional data and then feed it to the autoencoder, and we have 4 stacked autoencoders together, followed by a logistic regression for the classification. The results were about 98%. So as a conclusion, we have introduced here a recent comparison between supervised and supervised techniques for hyperspectral image segmentation, semantic pixel-wise segmentation. We discussed the available data sets for this task. We introduced some CNN-based work and other autoencoder-based work. And I'm ready for any questions if you. Thank you very much. Hello?
Yes, we can hear you.
Okay.
Any questions?
If there is any questions?
Yeah, if any questions are there from anybody, you can type your questions on the chat box. Anybody who wants to ask anything, please type your questions. Okay.
I think in the last slide I have shown my contacts. So if you have any questions, you can contact me on this emails.
Okay, so where from you got these data sets? Dr. Salim, this is a question from my side. What was the source of your data sets?
The data sets are available online. The link for the all listed data sets, the links for all listed data sets are in the paper. All data sets are free for use and available without any registration or any contract.
Okay, fine. Okay, so all these are freely available data sets.
Yeah.
Okay, fine. Fine, we can, thank you, Dr. Salim. Yeah, thank you. Thank you.
Professor Lavika, we can move to go back to Khawla Ishabi, the third talk.
Okay, sir.
Khawla, are you here? You hear me? Khawla?
Yes.
So you have the floor. You can give your talk on 10 minutes, please.
D'accord. C'est bon pour la présentation?
Yeah. But in English, not in French.
Mais j'ai préparé ma présentation en français.
No, please, Khawla, the attendees are not from Morocco only. We are attendees from more countries. And for example, Lavika is from the chair of the session. One of the chair of the session is from India. And she is not going to understand you. And more people from Egypt, for example, please try to do your presentation in English.
Is it possible to give your speech in English? Khawla?
Yeah, d'accord.
Khawla? Is it
Oui.
okay or not?
D'accord.
You can start, please.
Hmm.
If you have problems, we can move to the next speaker and coming back to you in 10 minutes.
Oui, c'est good idea.
Hmm?
Oui. Yeah.
Yeah.
Yes.
So, the next, Professor Lavika,
Yes, sir.
I think she has some concerns with the presentation.
Yes.
So we can move to the next speaker and coming back to her after 10 minutes.
Yeah, perfect.
Okay.
So, yes.
You have the floor, please.
Okay. So the next presentation is on the topic commodity image retrieval based on convolutional neural network and late fusion. So the presenters are Ziji Zhao, Hongji Zhang, Huadong Sun, and Baozong Kiao. So any one of you who's there? Ziji Zhao? Okay, Ziji Zhao or Hongji Zhang? Anyone? Sir, I think they are not there. Okay, so let us go for the next one. So the next presenters for the 8th paper, they are Hosam Harmaou and Professor Abdul Karim Haqiq.
Yes,
Hosam?
yes, I'm here.
Okay, good. So the presentation is on convolutional sliding window-based model and synthetic data set for fast feature detection. So you can take over, Hosam, and
Okay.
start presenting. Please share your screen.
Thank you.
Yeah.
Can you see my screen?
Yeah.
Yeah, we can see your
Yeah.
screen. One thing I would like you to remind, it's a 10 minutes presentation. So please
Okay.
try to wind up within 10 minutes and then we'll have a QA session, a short QA session.
Okay, thank you.
Okay. Yeah.
Okay, so hello everyone. So I would like to present to you our work entitled Convolutional Sliding Window Based Model and Synthetic Dataset for Fast Feature Detection. So let's start by defining the problem. So the aim of our research is to study future matching using deep learning methods. Future matching consists of finding the corresponding of several regions of an image of a scene in a model image of the same scene acquired from a different point of view. The following image shows an example of future matching obtained with our methods, which I will present here. Applications of future matching in computer vision are numerous: stereo matching, object detection, image registration, or augmented reality, which interests us in particular. So the classical matching pipeline has not changed even after the introduction of deep learning methods. It consists of 3 steps: detection of the features that correspond to real regions for matching, and description of features by vectors that are robust to variation, and finally matching by comparing the feature or the descriptor of the feature. So our main contribution in this study is to propose a new approach based on deep learning. So let's start by the stage of the art. The Hans detector is one of the first detection algorithms that is still widely used today because of its good corner detection performance. So, in fact, not all areas of the image are reliable for matching. For example, line and edge and uniform region are not locally unique, and therefore they are not reliable for matching. Whereas a corner is locally unique and reliable for matching. So the Harris detection therefore scans the image for corners by detecting strong intensity variation in all directions. There are also other methods like sit and serve, which are very popular also today. and which use the scale space theory for multi-scale detection and allow the extraction of invariant descriptors. There are also fast detection algorithms like FAST and OR. On the other hand, learning-based methods are not recent. For example, ACRC reduces the dimensionality of seek detector by learning the projection matrix. There are also CNN models for matching which compare the two patches which correspond to rectangular regions of the image. They compare the two patches to see if they correspond to the same feature. There are also CNN models for descriptor extraction. And more recent deep learning models like L2Net, HardNet, and SOSNet they use different architecture and different complex loss function sometimes for patch descriptor extraction. And more recently, there are also some end-to-end model like LIFT that use end-to-end model for detection and descriptor extraction. So our observation is that in all these methods, the training dataset is made up of patch extracted by handcrafted detectors, such as SIG. This is due to the difficulty of manually extracting with precision the position and the orientation of the features on the image. Considering that a single image can sometimes contain more than 1,000 of features. And the second observation is that the models needs to be colored for each patch, each rectangular region of the image. And this takes a lot of time to compute the feature of all the image. So to solve these problems, we propose to create a new synthetic data set for learning so that traditional and or handcrafted methods are no longer used. Then we propose a new convolutional sliding window model trained on this dataset for fast detection. Finally, we propose to extract the descriptors using the same model. So let's start by the synthetic dataset. So we create a first synthetic dataset, which we call the patch dataset. And we have created a dataset of two classes of patches, futures and non-futures. Futures correspond to corners and non-futures correspond to uniform region and edges or lines. So to increase the invariance of the detection to geometric and photometric variation, we augmented this dataset by varying the angle of the corners, the orientation of the patch, the contrast, the luminosity of the patch, and with the contrast with the background. We also added blur and noises. In total, we generate 237,000 patches. So with 112,000 futures and 125,000 non-futures. And from this patch dataset, we generated a mosaic image dataset. So the size of the image, mosaic image, is 560 by 420, which corresponds to a ratio of 4:3, which is the most widely commonly used ratio. These images will be used as input for our model. We have also generated future maps which correspond to the location of the future in each image and which we use as the output of the model. As the proposed model allows the detection of 40 by 40 patch with a stride step of 2 pixels, this gives us a future map with this size. So the non-future are assigned value of 0 in the future map, and the future are assigned value of 1 in the center, and their neighbors are assigned values less than 1 according to Gaussian variation. Indeed, the neighbors patches of the futures also contain a patch of the future and must not have a value of 0 in order to be distinguished from no future. We then consider also a corner as the intersection of patch as corner if we verify this condition of contrast. In total, we obtained 200 images with 1,200 patches per images. So we tested different architecture models. In a classification approach, we used the patch dataset, the first dataset, and we tested different artificial neural network from shallow to deeper and different and two CNN models. We don't keep all the detail, but we have used the review activation, sigmoid output, and the binary cross control previous function. So the major disadvantage of this method, of this approach, is the processing time. Since to perform the detection, we have to browse the image with a sliding window and call the model for each patch. So in order to overcome this problem of processing time, we used a convolutional sliding window model, which allows the model to be colored only once for the on-tier images. This consists of using a CNN which exploits the fact that neighboring patches have regions in common, and therefore parts of the information used for the calculation of a patch can be used by the neighboring patch. So the first image here illustrates this principle. Here we have an 8x8 image, and which we scan with a step of 1 pixel, resulting in an output image of 2x2. So we have therefore created the following model, which allows to detect future of size 40 by 40 by scanning the image with a step of 2. The architecture follows a similar pattern to that of the VGG16 model. We have the convolution, batch normalization, and review activation layers are repeated several times with different number of filters. And after we use the max Boolean operation and the valid padding, which determine the desired step of the sliding window, which is 2 in our case. And at the output, we apply a linear output and not a sigmoid, which is the case in classification, since it's no longer a classification approach, but a localization approach. This allows us a large variation interval in the future log. Finally, we use a sample mean squared error as loss function. We also created a regularization model using dropout, which consists of randomly removing activation units for each training example. So for training, we used Adam optimizer chosen for its speed compared to gradient descent momentum or RMS, which give equivalent results. The number of epochs is 50 epochs, which take about 2 hours on GPU. And the decrease, we use the decreasing learning rate between 0.1 and 110 or -5 to accelerate the conversions at the beginning. We use the 80% for of the dataset for training, 10% for validation, and 10% for test dataset. And here is the result of the optimization. So then we apply. Then we use this model for detection. Here we have the algorithms of detection. So we start. In fact, our model allows the detection of 14 by 14 patches. So in order to detect multi-scale in order to allow the model to do multi-scale detection, we use it. We start by applying a Gaussian convolution to eliminate features smaller than the desired scale. This is in fact the scale space theory used by many computer vision algorithms for multi-scale detection. So the same model trained on 14 by 14 patches can then be used for multi-scale detection. The only drawback here is that the model must be paired for each scale. Then we apply our model here to predict the future map. After we apply the threshold to eliminate no futures and noise. We can use a fixed threshold or percentage or other. And finally, we apply a non-maximum separation to detect the center of the future. Indeed, around the future, several other futures corresponding to the same structure are always detected. So only the local maximum is retained. We use the output of the first layer as a descriptor. To extract the descriptor, we use the output of the first layer as well. Generally,
Dr. Awesome?
Wait, yes?
Yeah, can you try to please wind up?
Yes, okay.
Yeah.
So here we extract future using the first layer of the model. We also try to make the future invariant to orientation and here we have the result of the evaluation. So we compare the different architecture of the NN and CNN. We have the perfect classification of the dataset, but a processing time of 160 seconds. The localization approach gives a similar result with a very low mean squared error, but a processing time of 200 milliseconds on GPU. We have a gain of 800 compared to classification approach. We also used tested the method for matching. We found the unique limitation is that the method don't perform very well on matching for when we have very large rotation. To conclude, we have presented a new method for future detection and extraction based on deep learning. The learning has been performed with this new synthetic data set, which allows to not rely on traditional methods as opposed to the stage of the art. The model allows a fast detection thanks to the convolutional sliding window techniques and allows a low error on the data set. The descriptor extraction can be done with the same model. However, the descriptor has still some limitation when the rotation is unfortunate. Among our perspective, we want to improve the descriptor by proposing other models. Also, we want to evaluate the method on other real data sets and on some application like augmented reality. Thank you.
Thank you, Dr. Hassan. Anybody in the audience who wants to ask any question, please type your questions on the chat box. Okay, I think no questions from anyone else. So I will ask one question. What was the purpose of testing with and without regularization? I could not get that thing.
What's the purpose of the regularization?
No, you have given the results with and without regularization in your presentation. So
Yes.
What is the purpose of representing the results with and without regularization?
Okay. Yes, in fact, the model without regularization here shows some overfitting. You can see that the error, we have a large gap between the test and the trained dataset. here. So we apply regularization, and we can reduce the gap. We can have the errors that are very similar between train and the test data sets.
Okay, so what was the original processing time? Since you have mentioned that there is a gain of 800, so that means the original processing time was in seconds?
Sorry, I don't hear very well.
I'm saying that you have written on this slide that the processing time is 200 milliseconds and that's a gain of 800. So that means the original processing time was in seconds.
The original was 160 seconds on the. In fact, we compare this architecture INN and CNN with different deep, and after we have our model that it's a different different approach, not classification but a localization. So in the first one, we give the model a small patch, and we have the classification of the patch, if it's future or not future. In this, in the new approach, we give the model an image, all the image, and they give us all the features in the output. So in the first approach, we have to scan the image with loops, with the sliding window to and detect, and for each patch we call the model to verify if it's future or not future. In the and it takes a lot of time on CPU. We use it on CPU because it is better to do sliding windows on CPU than on GPU. So the best time we can have is 160 seconds. And here we use it on GPU because we can have better time. So we have 200 milliseconds. I hope that does that answer your question.
Okay, yeah, fine. Okay, thank you, Dr. Hossam. We move on to our next presentation now. Thank you.
Thank you.
So the next presentation is by Fujian Chang and Governor David and Kuo Chi. So these presenters are here. Governor David, are you there?
Yeah, I'm showing it. I mean, presenting for them.
Okay, fine. Okay, so the topic of the presentation is convolutional neural network for fire
sure.
video image detection in the thermal power plant. So we welcome our presenter. You can start presenting. Please share your screen.
Okay.
Yeah.
As you can see, these are the authors, and we are all in Fuji University of Technology. There is the outline. We have the introduction, image of fire in video inspection process, convolutional neural network, degree of depth in neural network structure, and then we have the discussion and analysis. We have the recognition result, then finally the conclusion. So we start by introducing the project. So this is to present the mobility feature of fire to eliminate the interference of similar fire scenes, such as lightning, by using the change of fire coordinates before and after fire video of the thermal power plant. Now, this was proposed to address the issues of interference with look-alike, like features that looks like fire. So a look-alike fire scene in the recognition approach. So that is what we are working on. And then, as you can see, in the early fire detection process, the main focus was on flame detection. We have, which had three main characteristics. You have the motion characteristics, color pattern, and then the feature characteristics. And some researchers have done very well to really look into this. So now let's continue. We have this is the image of fire video inspection process. And as you can see, based on CNN, fire video inspection is in two sections. We have the model training and then we have the model evaluation. First, a high amount of fire image is collected for model training, and a deep CNN is used to obtain the deeper illustration of fire characteristics, and a large number of fire detection model. Now, the best model can be used to determine the fire and non-fire characteristics of newly imputed images. Yes, so as you can see here, we have the training CNN, that is the training data, and then we have the testing data. As I told you, it has two different categories. Then there's the real-time video feed that will feed information or data into the system. Then we have the when there's fire, an alert is sent. Data is sent to the control for carbon dioxide to be released, and when there's no fire, nothing happens. So let's continue. This is the convolutional neural network. As you can see, this is a deep network structure stimulated by the system of biological visual observation. However, the first deep learning network, which is the LeNet, was used to for handwritten numerical characteristics. Yeah. So let's continue on. Now we come to the degree of depth of neural network structure. So as you can see here, we have the first target detection is inspired by the idea of SSD. That is the single shot multi-box detection. Now, of which the sigmoid activation function is used to replace the activation function of the original network softmask to adapt to the binary classification problem of fire recognition. Now, the algorithm positioning method in this paper or this project is different from the sliding window method. It uses a single depth neural network to perform image detection, as clear as it is. Now, in the process of prediction, the network will generate a score of each existing target category and regenerate the positioning frame according to the positioning weight of the same time, matching the shape of the object more precisely to be able to distinguish or differentiate between the non-fire scenes and then the real fire scenes. And then the main advantage of this algorithm is in this paper is that it has a fairly fast processing speed without sacrificing accuracy. So without affecting the accuracy is also very, very good, and then which provides favorable condition for timely recognition of fire disaster. Yeah. So when we come to the scarcity analysis, now we used our computer, which is a STEM computer with a 16 gig internal memory, and then the training set is about 85. I mean, the images we have 85% to be the training set of the labeled images, which are randomly selected, and the test, the ones that we use to test, is just 15% of it. Now, to obtain high precision recognition result, as shown in the figure that I'm going to show you next, the bias of objects and default boxes are predicted at different level of the feature map, and the detection and sorting machine mark one input feature map of size 38 by 38 with 4 default boxes around each feature map element. Yeah, so that is what I'm going to show you next. And then as you can see here, this is the image for fire detection video image for convolutional neural network structure. It's well explained. So now we come to the recognition results. My images are black and white, as you can see. Now the fire images and the non-fire images are different scenarios are selected, as shown in the figure, as you can see. Now for the fire image, the models successfully identifies and locates the fire image for a similar fire image. Now, the model successfully determine the non-fire image, and the probability values of these images are shown in the table on the next slide. So as you can see, we have scene A, we have scene B, scene C, scene D, scene E, scene F, scene J, scene H, scene I, scene J, scene K, and then scene uh, um, I. So as you can see there. Now with these first 6 scenes are all with fire. From here, this, and that, they are all fire. If you look here, it's like a sunrise. This one is like lights on the street. This one looks like lights in the building. There's a light situated somewhere. This one to the same, and then this one, the next one is a sunrise, as you can see. So this is not fire, but this project is able to determine and then see if there is fire or not. So as you can see here, this is the partial fire or non-fire image probability values. So as I showed you, the first 6 scenes, as you can see, scene A, B, C, D, E, and F are all fire scenes. If you look at the probability, the probabilities are closer to 1, which is that there is a fire. Then the rest of the 6, there are no fire, it's a non-fire. Then the probabilities are farther away from 1, as you can see. So that is the probability values. Then now, when we come to the conclusion, as you can see, with the improvement of the processing ability of intelligent monitoring and control, to be able to determine and give quick signal or data for to the control system for them to see that there is fire and then action must be taken. We here the recognition of the disaster in the monitoring and control system has a positive significance for the control of the damage caused by fire. So there is a positive significance to be able to control the damage caused by fire with this system. Now, this article, as you can see, proposes a model that takes into account the accuracy of the fire detection and then the accuracy of its calculation. So it does its calculations very well with very accurate calculations to be able to determine and then differentiate between the non-fire and then the fire scenes. Now the model is inspired by the SSD algorithm, which is improved for fire disaster identification. Now, it has been proven through this experiment that the recognition model of this article can realize the recognition and positioning of fire disaster pictures, and it has a good recognition effect for detecting different fire disaster scenes and has very good generalization ability. Aiming at this problem that similar fire scenes interferes with fire detection in recognition methods. The article uses this article or this project uses the mobility features of fire to present a method that combines the change of the fire coordinates, fire coordinate position of the front and back frame of the fire disaster video. And this helps in eliminating the interference detection of the fire light scene, that is the non-fire scenes. In subsequent research, the current frame detection model can be further adjusted, and that was stated in this project, to detect smoke and frames and deal with the more complex situations for saving lives out of fire outbreaks. Thank you very much for uh, the presentation. And this is the end of my presentation. Thank you very much.
Okay. Thank you. So any questions from anyone? Okay, I also do not have any questions. So thank you very much for your presentation. And then, yeah, thank you. So let's move on to the next presentation now. Next presentation is by Hadir El Sadavi, Manal Tantavi, and Hovda Shadid and Muhammad Tolba. Are you there? Any one of you, any one of the presenters, are you there? Hadir, Manal, Hovda. Hello?
Do you hear me?
Yeah.
I think it's these authors are the same for
Yes,
the two previous papers.
Yes. I think so. They are the one. They are the same ones who had presented the presentation in French.
I think yeah, Haula is now ready and she can present, give you her talk.
Okay, fine.
No, I can present in English.
Okay, fine. So you want to present, Hoda?
Yeah.
Now?
No, yeah.
Okay, fine. Okay, so you can share your screen and start your presentation. So you'll be presenting which paper? Paper 1 stage versus 2 stage deep learning method for bone abnormality detection, or you will be presenting the earlier one, that means the deep learning method for bone abnormality detection using multi-view X-rays. So, yeah, so you're presenting which one?
I am ready.
Pyramid network for COVID-19. She is the author, the first author. The second talk for this morning.
They are okay. So you can begin your presentation. We'll figure out.
Yeah.
Okay.
So in this presentation, I will present our work, future pyramid network of COVID-19 pneumonia detection from chest X-ray image. For introduction.
Okay. In the authors, you have not been mentioned. For this paper, I think there are 4 authors. This is the second paper, and there are 4 authors: Khawla Echabi, El Mauktar Zemori, Muhammad Diomi, and Salsabil Hamdi. So
yeah.
you are presenting on somebody's behalf. You are not mentioned as one of the authors in this paper. Hello.
Oui. Yeah.
So.
Hello,
Okay.
Ivika, do you hear me?
Yeah, I can hear you.
This is Khawla Hamdi, Khawla Ishabi. She is the first author of this paper.
Okay, sir.
She is one of the 4 authors of the paper. She is the first author.
Yes. Now I got it.
And I am El Mukhtar Zamouri, the second author.
Okay, no problem. Yeah, I think some confusion was there because the same pronunciation author Hauda was also there in the third paper, so some confusion was there from my side. Okay, you can continue.
Yeah. Intelligence artificial is a discipline that has continued to evolve since the middle of 20th century. Many changes have appeared to perfect this very promising technology developed with the aim of one day sense to emergence of perfect between human and machine. Yeah, cluster algorithm allow data to participation and subgroup and cluster in a supervised manner. This subgroup together similar observation clustering algorithm. Therefore, strongly it depends on how to define the notion of similarity, which is often a space of the field of application. application in intelligence artificial is marketing. It can be used to characterize and discover customer segments for marketing. To biology, it can be used for classification with different species of plant and animal. Tree is library is used to group different book to basic of.
Carla, 1 minute. Sorry to disturb you, but you are presenting in French.
No.
Is it that?
I'm present in English.
Your presentation is in English only, right?
Yeah.
Okay. Okay, then go ahead.
In December 29th, a cluster of pneumonia case of noun caused in the city of Wuhan in China has been reported to the World Health in January 2020. A new and previous unknown virus was undefined. Letter number 29, the 29th novel coronavirus, and sample obtained from case and generate analysis of the virus interacted. Alors, analysis of need. One, c'est automated detection based on algorithm. Two, applied to CT and X-ray image. Three is discriminate COVID-19 decide from other accurate pneumonia. Four is validation of model bewitch and using data. Alors, so for problematic, currently, a mini-clinic method is used for the diagnostic of COVID-19 detection of viral gene by the RT method. It's for the most widely used. The problem with it is with this method, it's that only a limited number tests could be performed each day, making it difficult of other to obtain consistent data on the prevalence of the virus and to monitor the situation in real time. This had created an urgent need to develop a method that's automated of detection of COVID-19 and the discrimination between pneumonia caused by the coronavirus and other type of pneumonia. So this solution is artificial intelligence. We propose to develop a deep learning model to automate the detection of COVID-19 for chest X-ray of symptomatic individual. The data set we have used in the article is collected by a team of researchers from Qatar University and Dhaka University, Bangladesh, and as well as their collaboration from Pakistan and Malaysia on collaboration with doctor. The dataset called is the COVID-19 X-ray database containing image of chest X-ray for COVID-19 positive. In case I will as image of normal and viral pneumonia. This image dataset is published available to Google and is currently updated with new X-ray image and person with COVID pneumonia. Also, in the table, the version we used in the article consists of one town hand. 1,208 and COVID-19 positive and image and normal image and variable pneumonia image. For l'architecture, our proposed deep learning architecture is based de ResNet and pyramid function network. ResNet is backbone of network, and VPN is future extraction network. The proposed deep learning architecture for the classification of child X-ray image with three classes: COVID, pneumonia, viral, and normal pneumonia are used in system. To address the problem of detection of objects on different scale, the idea is to use a pyramid, and some images are different scale, so that the network is able to learn the characteristics of the same objects across a wide range of scale and in a dataset. To evaluate the performance of our model and compare its different deep learning algorithms, we used for performance metrics, which are precision, recall, and F1 score and precision. The results obtained show that our proposed architecture outperforms other deep learning algorithms based on the transfer learning. In particular, our model improved the COVID-19 detection performance, since the COVID detection F1 score is for F1 score is 99. Is 99. It's true for my results with this travel.
شكرا.
D'accord. Pour conclusion, it's the paper which proposed a deep learning model based on ResNet and future pyramid network of for automatic COVID-19 detection of pneumonia discrimination from X-ray image and offline. C'est tout.
That's all?
That's all, yeah.
Questions, please.
ازيك عامله ايه؟ ماشي. انا عندي اكتر من حاجه. عندي حجز مع الدكتوره.
Please mute your phone when discussing with others. Thank you. Questions, please.
كتيرة عندي دي، وعندي المتابعة بتاعت التغذية.
Please, could you mute your phone? Please.
الروشتة الأخيرة لا مفيش، ما بيدينيش من بقاله فترة وكل مرة. هي دي.
Professor Lavika?
Yes, sir.
I think we can move to the next speaker.
Yeah. We definitely move on to the next one. So our next presenters are Hadir El Sadavi, Manal
المتابعة يعني أنا أخدت الأولانية خالص النهاردة الثالثة.
Muhammad KH, can you please mute yourself? Muhammad, please mute yourself. Okay, fine. So let's move on to our next presentation. The speakers are Hadir Sadavi, Manal Tantavi, Hauda Shadid, and Muhammad Tolba. Are you there? Any one of you? Any one of these people? Are you there? Hadir, Manal, Hauda, and Muhammad Tolba. Okay, I think they are not there. So let's move on to the next one. Are these presenters here? Muhammad Ali, Mariam El Berry, and Zaki Taha. Are you there? Muhammad Ali, Mariam El Berry, and Zaki Taha. Anyone of you is here? Okay. Ahmad Y. Lotfi, the last presentation, Ahmad Y. Lotfi, Ala M. Zaki, Tariq Abdul Hafiz, and Tariq M. Mahmood.
Yes.
Okay, fine. So we'll begin with this presentation, and the topic is privacy issues of public Wi-Fi networks. So Ahmad, you can share your screen, please, and start presenting.
Welcome to all conference participants.
Yeah, please share your screen.
This presentation is visible to all participants. It's visible to all participants. Hey, this presentation is visible.
Yeah.
Please make it full screen. Yes, you can start.
Welcome everybody. At first, I would like to express my good feelings about participating in the International Conference on Artificial Intelligence and Computer Vision 2021, and would like to welcome all participants, organizers, and conference chairs for their continued support. My name is Ahmed Yahya. I will be presenting the research paper, Privacy Issues of Public Wi-Fi Networks. And this research was also conducted by Dr. Ala Zaki, Dr. Tara Abdul Hafiz, and Dr. Mustafa. Outline, introduction, objectives,
Sorry, Lavika.
Yes.
Please ask attendees to mute their mic.
Yes, sir. I have asked them. Please, others, all of you, please mute your mic. Anybody else who's not muted their mic, please mute your mic. I think, sir, all of them are muted except the speaker. I think it is fine.
Sorry.
Yeah, you can continue.
I have some problems in the network. I sent the presentation record. Outline, introduction, objectives, methodology, experimental result, discussion and limitation, conclusion.
Ahmed, we are
Yeah.
not able to see your PPT. Please share your PPT.
Yeah.
Yeah.
Yes.
Welcome everybody. At first, I would like to express my good feelings about in the International Conference on Artificial Intelligence and Computer Vision 2021, and would like to welcome all participants, organizers, and conference chairs for their continued support. My name is Ahmed Yahya. I will be presenting the research paper Privacy to Public Wi-Fi. And this research was also be conducted by Dr. Ala Zaki, Dr. Farah Abdelhafiz, and Dr. Tarek Mustafa. Outline, introduction, objectives, methodology, experimental result, discussion and limitation, finally conclusion. Introduction. Public Wi-Fi hotspots are becoming extremely popular around the world. Most people also connect to hotspots because of their free of cost service. According to semantic research performed by According to the semantic research performed by 15,532 consumers across 15 global markets, 46% of participants don't wait more than a few minutes to connect to the Wi-Fi network after arriving at an airport, restaurant, shopping center, and hotel or similar place. By comparison, 60% of participants are unaware of the risks inherent with the use of untrusted network and feel that their personal information is secure. We are living in a technological society and are seeing a rapid rise in internet connectivity to public networks. The number of Wi-Fi access points distributed had reached 94 million globally and is expected to increase to 549 million by 2022. This increase is guided by the spread of new computing devices. About 3 billion smartphone users globally in 2018. Objectives. Examine the user's awareness of public from activities such as web browsing, search engine querying, and use social networking. The second goal for this paper helps the university decision makers to consider the interests of public Wi-Fi users to open or close those frequently searched sites within the university domain and to make the ideal use of university resources. Methodology. To examine the privacy in public Wi-Fi, we propose an experiment that consists of 3 phases. The first phase set up a public Wi-Fi. The second phase collecting user traffic, and the last phase analyzing the collected data. The flowchart of the proposed experiment has been shown in this figure. Setting up. We collaborated with the Information Technology Center in Mini University, which providing large-scale Wi-Fi service for students, employees, and teaching staff. The admin of the center has allocated for our experimental 3 hotspots. Make it public, and they were provided with internet service through a specific server to monitor the traffic of users which use the internet through these hotspots. We installed Wireshark on the Windows server as shown in figure. We set up our experiment of 3 public Wi-Fi networks, hotspots, and various locations and times in many universities. After the participants had connected to the internet via our public Wi-Fi traffic, routing from the participant device to the internet via our experimental Wi-Fi network were captured by Wireshark. Then the collected data saved as backup files on the permanent memory of the server. Every interval of time, twice every day, and collected these files every 3 days. The data has collected in 1 month from November to December 2020 with 1,295 users. Analysis collected data. We developed a model using the Python programming language to analyze the collected data. This model analyzes the data in two steps. The first step, we parse recap files to extract the data and the header of HTTP, DNS, ICMP, SMTP, and POP3 for traffic routing from the participant's device to the internet. Then save this data in CSV files as records. We used a unique record for each user, where we identified a unique number for each device connecting to our experimental Wi-Fi networks by using the MAC address and the device name, such that if any device connected to our experimental Wi-Fi more than once, it is considered as the same user. In the second step, we analyze the data in the CSV files to extract the best website and any user's privacy leakage. Experimental result. We describe the result of analyzing the collected data from users that connect the internet via public Wi-Fi network defined for our experimental. We organize this description in two parts. In first part, we describe the result of analysis-based website, and the second part, we describe the result of examining the privacy leakage. Result of analysis-based website. The number of users who connected to the internet via the public Wi-Fi network is defined for our experimental is 7,295, and this user visited 2,721 different websites. We classified this website into different 29 categories by using the machine learning model. 28 of which are popular, and the sites that don't belong to these common categories are then classified into a category called other sites. Each category contains a group of different websites. This figure shows the top 10 categories that contain a top number of websites. To determine the highest categories according to the number of visitors, we counted the number of users who visit each category, such that each visitor was counted only once. We found that the highest category in terms of the number of visitors is social network. This figure shows the top 10 categories according to the number of visitors. From this figure, we note that the second highest category in terms of the number of visitors is other sites, which contain sites that don't belong to the common category, which means that they are not required for useful sites for users who belong to the university, or that the use of these sites for access to it may affect the performance of university information network. Therefore, this report can be useful to the university network admin to open or close those frequently used sites within the university domain, and to make the ideal use of university resources. We assign a number of each connected to the Wi-Fi networks using the MAC address and the device name. So it was easy for us to track a specific user, like sites he visits frequently, and his data is under privacy leakage. We took 10 random users and tested the sites they visited frequently. This table shows this data, and this data are visualizing in figure 5. Discussion and limitation. The user must bear in mind that the public Wi-Fi networks are completely unsafe, so they must avoid internet sites that need sensitive personal information, such as the credit card numbers and data for accounts on different sites. We will provide some tips you should avoid using these networks to accomplish this goal. The user must disable the file sharing features, so the user should note that it is difficult to control other users on the same network, but at the same time he can control his device and what he shares. So whoever uses it can Windows-based devices can cancel file sharing on the network. You should be activating the internal firewall in Windows to limit any external connection. Care must be taken to install and update protection programs. VPN service should also be used as it is one of the distinctive ways that can be relied upon by making the connection encrypted through a virtual network and then connecting to it through the public network, which means using a VPN which gives the user greater security and ensuring it doesn't steal private and sensitive data. Limitations. There may be more privacy. There may be more privacy leakage from sharing data over our experimental Wi-Fi network, but the keywords used to filter the data during analysis may not satisfy that. Among the difficulties that we encountered was the failure to establish public Wi-Fi network in area outside the university. Conclusion. We proposed experimental to examine the privacy leakage from using public Wi-Fi in many universities, which contains 16 different faculty, and help the admin of University Information Technology Center to consider the risk of public Wi-Fi users to open or close those frequently searched sites within the university domain and to make the ideal use of university resources. Our experimental week collaborated with the Information Technology Center to allocate 3 hotspots, make it public, and they were provided with internet service through a specific server. We collect data 7,200 connect via public Wi-Fi of our experiment from 20 November to 20 December 2020. After analysis this data and classifying the best website using machine learning model, we extract reports which show that 85% form the users use an unwanted links category other sites, which may cause the network doesn't work either, and 90% of the users use social network category and 60% from the users use search engine category. We examined the privacy leakage. We found some privacy data are leaked, such as the user name, mobile number, email, and user ID. Thank you.
Okay, so any questions from your side, from anyone? Okay, so no questions from my side too. In that case, we can move on to the pending presentations. Professor Brahim.
I think there are 50% of authors are not with us.
Yes, sir.
So it is, I don't know why. Is it perhaps for timing or chosen timing or what? What do you think?
I don't know. Perhaps because they know first that their papers are already published in Springer books,
Yeah.
but but unfortunately, yeah.
But what is important in a conference is
exactly to present
and to discuss.
Yeah, exactly.
To get new ideas and future works and so on.
Sure. But otherwise, I thank you so much, Professor Brahim Ubi and Professor Malika Jouel, for sharing these first oral sessions on deep learning and IoT. And thanks also for all the authors who are presented their papers. Then now we have a break of 2 hours, and we will come back at 3 p.m. time in Morocco we'll have the second plenary speakers at 3 p.m. and at 5 p.m. we'll have the second session. Okay, I hope we can see you all with us this afternoon, and thank you so much for all the attendees, and take safe, and see you soon this afternoon.
Thank you.
Yeah. Thank you, Professor.
You're welcome.
Thank you, sir.
No, thank you so much.
See you.
Professor Abu Ala, you are here. Professor Abu Ala, you are here. You are welcome, Professor Zmouri. Nice to see you with us this morning.
Thank you, سي حقيقة.
You're welcome.
Thank you.
You're welcome. You're welcome, Wafa. Thank you so much. Professor Abu Ala, you still with us? You welcome, Naima. I don't know, Professor Abu Ala. I think Professor Abu Ala is not here. Then we can, okay.